Okay, so let's talk about uniform convergence and integration first, and then differentiation. So let me kind of draw a picture, and we'll see if we can figure out how uniform convergence and integration are going to work out. So let's say the function that we're trying to take as a limit is f, and then let's draw a little epsilon neighborhood around f for uniform convergence. So I've got this little band of size width epsilon here, and then no matter what I do for my sequence, the functions that approach f have to eventually be in this little epsilon envelope. They can wildly move around inside here, but as that red envelope gets smaller and smaller, all of the functions eventually have to be inside that little red envelope. And so the area under the curve can't be that far off under the green curve than the white curve, because sort of the area under the white curve, let's go from say A to B, is this, right? And so B minus A times epsilon, well, times 2 epsilon would be how much is in the red band. Well, if the area under the curve of f is finite, I can get at most the area under the curve plus epsilon times B minus A. And I have to have at least the area under the white area, let's call it I. So the green area sort of has to fall between I plus epsilon times B minus A and I minus epsilon times B minus A. And as epsilon gets small, that green area actually has to approach that white area, because B minus A is a fixed value. So if I can make epsilon really small, then this green area is bounded really close to the white area. Okay, so that's going to be our first theorem, is that integrals play nicely with uniform convergence. So theorem, let's write this down specifically. So let's let f sub n be integrable on AB for each n, and suppose f sub n converges to f uniformly. Then f is integrable, and we get this limit, the integral from a to b of f dx is equal to the limit, as n goes to infinity, of the integral from a to b f sub n dx. So it's not only integrable, so uniform continuity gives you that the limit is integrable, and uniform convergence gives you the limit is integrable, and that it's what you would expect it to be. It's the limit of the integrals. Okay, so let's prove this, and the proof kind of follows that picture that we drew. So let's have epsilon sub n equal the supremum over x in a to b of the absolute value of f sub n at x minus f at x. Okay. So I get a different epsilon. Epsilon sort of how far away is f sub n. Then we get that f sub n at x minus epsilon is less than or equal to f at x is less than or equal to f sub n at x plus epsilon for each x in AB. Okay, so the lower integrals and the upper integrals, we get the integral from a to b of f sub n minus epsilon dx is less than or equal to the lower integral of f dx from a to b, which is less than or equal to the upper integral of f dx from a to b is less than or equal to the integral of f sub n plus epsilon dx from a to b, i.e. the difference between the upper and lower integrals of f in absolute value is less than, well, I can pull off this constant outside and I get the integral of f sub n, and I can pull this constant outside the integral of f sub n. This is going to be 2 times epsilon times b minus a. Okay. Because we can make epsilon as small as we want, we can make the upper integral and the lower integral as close as we want. This implies that, let's go back to white. This implies that f is integrable because the upper and the lower integrals we can't tell apart, so they have the same limit. Okay. Now I actually have to show that it's what we want. Okay. So what happens here is, because epsilon sub n goes to 0, by uniform convergence, what we can do is we can look at this statement again. Let me call it star. This statement here says that when I can replace this stuff in the middle by the actual integral from a to b of f dx, and these were epsilon sub n's, what I can do is I can compare this guy to the integral of f sub n, and it's going to be within epsilon times b minus a of it. And by star, we get that the integral of f dx minus the integral of f sub n dx in absolute value is less than epsilon sub n times b minus a goes to 0. So the integral from a to b, these are from a to b as well, of f dx equals the limit as n goes to infinity of the integral from a to b f sub n dx. Okay. So that shows that integration plays really nicely with uniform convergence, right? So if I have uniformly convergent functions, the integrals are also convergent, and they're what you expect them to be. Okay, so let's try and take a look and see what happens with differentiation. We'll kind of draw the same picture. So I've got this function f, and we've got, say, here's a and here's b, and we've got this envelope of width epsilon around x. And now I'm going to take just an arbitrary function. I'm going to kind of draw it a little bit messy. So maybe it's perfectly fine here, but then once it gets inside a and b, it shoots straight up and straight down, and it wiggles really fast in between here. Now maybe this is smoothly differentiable, but the derivative is pretty crazy in there. Okay, but I can still do this. Maybe this is f sub n, and maybe when I go to the next one, I've shrunk my envelope down a little bit, but I get just as crazy, but still differentiable. Okay, these derivatives, I can't put any sort of bound at all on how big or small the derivative can be. Right? This can just be wild inside this envelope, straight up and down almost. The derivative can reach positive infinity and then negative infinity, and can be all over the place. I don't have any control over the derivative because of the envelope. Right? If I go back to the picture where we had the integral, it didn't matter how crazy this function got inside here. The area under it was still bounded by the red envelope on top and the red envelope on bottom. Right? I did have a lot of control over the integrals because of the envelope. I have zero control over the derivative because of the envelope. The derivative can just go crazy. So that's kind of the reason why it doesn't work very well to say, we would like to say the same sort of theorem. We sort of want to say, but can't, that if f sub n converges to f uniformly, then if f sub n is differentiable, then sort of and if f sub n is differentiable, then f is differentiable, and f sub n prime goes to f prime. But we can't do this. This is not a true statement. We have zero control over how big these f sub n's are. Even if derivatives are, we have zero control over f sub n prime. Even if we know that they're differentiable, we have zero control over how big or how small that derivative would be. That's kind of the problem. So what we have to do is we have to put a lot more restrictions on our theorem to link convergence of functions and derivatives. And I'm not going to prove this theorem, but I am going to state it. The theorem is pretty technical. It's going to be Theorem 7.17, and you can try and read through it if you like, but it is fairly technical, and there's a lot that you kind of have to remember. The book does a pretty good job about going through it. There's a few points that you might have to think about pretty hard, but let's just state it here. Okay, suppose f sub n is a sequence of functions that are differentiable on AB such that f sub n of x naught converges at some point in AB. So we're not saying these f sub n's without the derivatives converge at all. We're just saying we have a bunch of differentiable functions. and at one of the points they do converge. So I've got pointwise convergence somewhere for the f sub n's. Okay, the rest of it is if now the derivatives f prime sub n converge uniformly on AB. So now I've controlled how wild those derivatives can be. The derivatives can't be very wild at all because they're going to converge uniformly. Let's say they converge, then the actual f sub n's also converge uniformly. And say on AB, and what we want happens, and f sub n prime of x equals the limit of the f prime sub n's of x as n goes to infinity. So not only do they converge uniformly, their limit is differentiable, and their limit that's not an n. Let's say to f. So they converge uniformly, they converge to f, f is differentiable, and it's the limit of the derivative, so it is what we want. But what we had to do was we had to control how wild those derivatives were, right? We controlled how wild the derivatives got by using that the derivatives converged uniformly. Okay, so it's sort of like the integration thing, right? I start with the bottom function and I go up to the top function, and that works out fine. Okay. Or sort of I start out with the derivatives of the function, I go up to the integrals and the original functions, and I get uniform convergence. So I don't really want to go through that too much. We're going to work on power series next and see how derivatives and integrals of power series work together, and then finally put it all together and get Taylor series stuff tomorrow.